So, uh, welcome to the final week of circuit for analog circuit analysis for analog designers. That is week 12. So, in this week, a few problems for non-linearity through current injection analysis of non-linearity through current injection were covered. Apart from that, the recap of the summary of the complete course was given. So before we start with a few problems on analysis of nonlinearity through current injection, do you people have any specific doubts over the complete course? So Thalpa side, do you have any general doubt or any other doubt like across the course that you have or any topic that you want can be revisited or something like that?
Yeah. Yes, sir. I think week 11, sir. Week 11 only, sir.
So week 11, like
Oh no,
what
no,
is
sir.
the
Week 12 is sufficient. Week not week 11, sir. Week 10, I think.
week 10? So what was the topic of week 10? The transmission line, is it?
Yes, sir.
So what is your issue? Can you explain the issue? Like any specific problem or any specific concept?
No, sir. Sir, for week 9, I performed very well, sir. I thought I gave my 100%, but I got 40 marks only. Could you please tell me, sir, where I may have done a mistake, sir? I will show my
Uh,
presentation, sir.
that is not possible. Okay,
I will. I'm appearing for final exam also, sir. That's why.
just a minute. Let me present the assignment of week 9. I can go through the direction of solutions for that, and then we'll see. You can see my screen, right?
Yes, sir.
The computer screen.
Yes, sir.
So uh, it's mainly for to find the uh, S parameter matrix. For two of them, it is finding the S parameter matrix. So I think this should be straightforward now from the analysis. Do you have any problem in problem 1 and 2?
No, sir. I perform well only, but how the evaluation means a final exam also the same evaluation will be taken place now. I would like to know what are the things I need to correct it.
No, you performed well, as in performed well. How? Like, were you getting the correct answers?
Yes, sir. I think week 9 I get a correct answers. I'm
Uh,
sure.
so,
From week 9 I am confident, sir. The rest of them I don't
like,
say.
I'm not saying that. So you are getting correct answers and you are performing well. So, what is the issue then?
Yes, sir. But I don't know what's the mismatch, sir. If I correct it, I have to correct it, sir, for final exam. That's why.
No, you got the evaluation. You got the answer sheets after evaluation. No. So what is the problem?
No, sir, I didn't get any answer, sir. I mean, we assignment solution I didn't get, but I get the marks scorecard. Exam is getting. I
No,
think exam also exam center
that
also. Getting.
that you are asking very very general doubt, man. I can't go through all of your answer sheets and uh, explain every problem. If you have any doubt in one specific problem or any concept, that you can tell. Otherwise, we can continue with the course, with the week's problem.
Yes, sir. Okay. Sir, yeah, continue, sir. Sir, okay, continue, sir.
Okay then. So my screen is visible, right?
Yes, sir.
So we were talking about current injection. Yeah, we were talking about current injection. So we will try to implement this analysis on some popular filters or some popular circuits. So the first thing that will and basically we will try to implement it on feedback systems. So the first one that will take up is the inverting amplifier. So this is the output, this is V in, and this is grounded. Okay, so in this case, if you see, had the op amp been ideal, so what would have happened is, had the op amp been ideal, just a minute. Yeah, sorry for the disturbance. So had the op amp been ideal, V out would have been minus RF by Ri times V in. Now let's replace this ideal op amp with a voltage controlled current source. So we will replace it with this. So this is the negative terminal, and yeah. So okay, can you tell so let's say this is the op amp. something like this. So can you tell which will be the positive terminal, which will be the negative terminal? So out of these, which will be the positive one?
Sir, upper side will be positive and lower side will be negative, sir.
Are you sure? How do you calculate that?
It's equivalent circuit, no, sir.
No,
Voltage.
no. See, like the way to calculate it is, suppose you increase the voltage at this terminal. What will happen? This current, let's say this is GM, this is
VG.
V1, this is V2. Okay, this is, and current here is
V1, G into V1 minus
GM into uh,
V1
some V1 minus V2. Okay, now if you increase this voltage V1, what will happen to this current that is going down? This current is going down, that is GM into V1 minus V2. So if you increase this voltage, what will happen to this current? This will increase or decrease?
Yes, sir, it will increase, sir.
Yeah, it will increase. Now if some current is being pulled out of a node, what will happen to the voltage at this point? So the current is being pulled out of this output node, V out. So what will happen to V out? Will it increase or decrease?
If it is pulled out, it will decrease, no, sir. Output voltage
Yeah,
will
it
decrease.
will decrease. So you are increasing the voltage at V1, your output is decreasing. So this is the negative terminal and this is the positive terminal. Okay, you get it?
Yes, sir. Yes, sir. Continue.
So we'll replace this with the voltage current voltage controlled current source. So how will the circuit look? You will have input resistance as Ri. This will be the negative terminal. Let's call this terminal as Vg, and this will be grounded, and this will be some Gm times Vg, and this will be Rf. Okay, and this will be V out. So now now what will happen is that instead of having this Gm times Vg, this will have third order nonlinearity also. So let's call this as G3 times Vgq. Okay, now you have to find the value of V out. What is the value of V out? So what is the first step in current injection method?
Sir, first we need to find out the first order while making G3 equal to 0.
Okay, so G3 you will put as 0. Okay, and you will find the voltage values at all the points. Okay, so how you can find it? One straightforward way would have been do the complete math and then find the value. Okay, like that is like basically in this circuit it will work because in this circuit there are not too many of the components. But in large circuits that technique won't work. Okay, so there is an easy way to find approximate voltages. So let's say this GM is very high, and this GM being very high is so that the loop gain is very high, and if the loop gain is very high, the voltage at the output will reach the ideal op amps value, that is Rf by Ri times V in, correct, minus of Rf by Ri times Vin. Do you agree?
Yes, sir.
Okay,
Inverting
so
gain. No.
so Vi and this is Vg. So this is Gm times Vg, and this voltage output. What this you know that this voltage is approximately equal to minus of Rf by Ri into Vn. Correct?
Yes, sir.
Okay. Now, what comment can you make about this voltage's magnitude? So, what will the current flowing in this direction? This voltage is Vg. This voltage is minus R. This voltage is V out. That is approximately equal to minus Rf by Ri times.
V naught
So,
minus Vj by RF, sir.
this current will be I will be equal to V naught minus Vg by Rf. Correct?
Yes, sir.
Now, what comment can you make about V naught's value and Vg's value?
Yeah, V naught is already value, sir. We need to find out that magnet. Yeah, we need to find out the value. Minus RF by R1 into input voltage. VG.
No, what I am saying is like if you compare the relative magnitudes of V naught and Vg, can you say something for sure? Like I have told here that Gm is tending to infinity. Let's say. So, what can you say about relative magnitudes of Vg and V naught? Or I should not say GM is tending to infinity. Basically, loop gain is pretty high, and loop gain being pretty high, what is the loop gain? Loop gain will be GM into RF plus RI into RI upon RF plus RI. Okay, and this will be equal. This is the loop gain, and this will be equal to GM times RI. So what I'm saying is this is much greater than 1. That means GM is much greater than the input 1 by input resistance. Do you get it?
Yes, sir.
Okay. So if this is the case, so what comment can you make about relative magnitudes of V naught and Vg? So you ideally what this Vg should have been. What should have been the Vg of the value of this Vg had the GM been equal to infinity, or GM was tending to infinity. Let's say if GM was tending to infinity, what will be the value of Vg? What will Vg tend to?
Yeah, VG will be VI minus. Yeah, it could be
What
top.
will what will be tending to? I'm asking. I'm not asking what will its exact value will be. I'm just asking what will it be tending to. If GM was tending to infinity, to what value Vg will tend to? What is Vg? In an ideal op amp, what is Vg?
Open loop gain, sir.
No, see, this is Vg, right?
Ah, yes, sir. Virtual, yes, zero.
0. Okay, so Vg will tend to 0. That means you can say is that V naught is much greater than Vg, because Vg's value is almost negligible, and V naught will basically its value will be equal to Rf by Ri.
Yes, sir. Yes.
Okay, so this current can be written as V naught by Rf, correct?
Yes, sir.
Now, if this is V naught by Rf, what is this is basically equal to V naught by Rf, and this current should be equal, right?
Yes, sir. KCL current. Yes.
Yeah. So minus of Gm times Vg. should be equal to V naught by RF. Sorry, V naught by correct, V naught by RF. Agreed?
Yes, sir. Mm.
Approximately equal to, because actually it should be V naught minus Vg. So yeah, so Vg is basically equal to minus of VRF times Gm.
Yes, sir. Mm.
Okay, now this is equal to, if you substitute the value of the V naught, so what will it be? It will be Vi upon Ri into Gm, correct?
Yes, sir.
Hmm. So if this is the case, so you have found the value of Vg. Do you agree?
Yes, sir. Mm.
Okay, this, like in this case, it so happens this is the exact value also, but as the circuit becomes more and more complex, this won't be the exact value. However, approximately the value you calculate with this technique and the value that exactly comes will be more or less equal. Okay, provided that the loop gain of the feedback system is high enough. Do you get this?
Yes, sir. Yes, sir.
Okay. So what will be the case now? So you have the value of Vg. Now you will short the input. You will have Ri over here. You will have Rf. This will be equal to this will be Vg. So this will be Vg hat now. This will be different than the previous Vg that we got, because now I've shorted it, and now I'm going to inject the current at the output. Okay. So this will be Gm times Vg hat. And what will I inject over here? So in which direction? First of all, which direction that injection will be up? Going. So basically, it will be injection, or like going up or going down. So this was the equation. This was G plus G3 into Vg cube, which was being pulled out of this node. So the same thing will happen over here. This will be equal to G3 into what is Vg cube? So this is so minus will go away because minus was there in both of them. So G3 into Vi cube by Ri cube into Gm cube. Okay,
Yes, sir.
get it?
Yes,
Now,
sir.
if Gm is so now this current will divide itself in this branch and this branch. Okay, you get it?
Yes, sir. Means at that point, current will be added now. RF
Yeah.
it will be added.
Now, if Gm is very large, if this Gm is much greater than Ri, so what will happen is this will, like, ideally this should have been a short this ideally, if Gm was infinite, what would have been the input impedance looking in Z? If if Gm was tending to infinity, what would have been the input impedance looking in? Sorry, the output impedance looking in.
Uh, Yeah, it would be infinity, sir.
No, not infinity. It would be zero. This is non-inverting amplifier, right? Non-inverting amplifier is a voltage source. Basically, it converts input voltage to output voltage. Ideally, for a voltage source, your output impedance should be zero.
Yes.
Okay. So if this is the current, let's say IO, and this is the current, this is IR. So like even so if as long as this approximation, that is GM is much greater than RI, is valid, what will happen is IO will be much greater than IR. Okay, and if this is the case, like you can neglect IR, and you can just say that IO is approximately equal to whatever the current this is pushing in, so or injecting or pulling out. In this case it is pulling out, it is equal to minus of G3 into Vi cube upon Ri cube into Gm Gm cube. Okay, do you get this?
Yes, sir. Yes, sir. Totally. Mm.
Okay, so now if this is the current that is being pumped into the system, so sorry, this is G3, not Gm. So now if this, so this is also equal to, what is this also equal to? Gm into Vg hat. Okay, because this is the voltage controlled current sources current. So Vg hat from here we get as approximately minus G3 by Gm into Vi cube upon Ri cube into Gm3 Gm cube. Okay,
Yes, sir.
get, do you get this? Now if you know the value of Vg hat over here, so if Vg hat, you know what is the current that is flowing over here, it is Vg hat times Ri, correct? And if this is Vg hat times Ri, what will be this current? This will also be Vg hat times Ri. So what will be the voltage here at the output? That is VO3 will be equal to 1 plus Rf by Ri, sorry, Vg hat by Ri over here, sorry, 1 plus Rf by Ri into Vg hat. This will be VO3. Okay, so VO3, that is the voltage at the output, is equal to 1 plus Rf by Ri into G3 by Gm into Vi whole cube upon Ri cube into Gm cube. Okay, so here you can see, if you increase the loop gain by a factor of, let's say, alpha, by what factor? So this was the loop gain, right? This, as we saw previously, this is the loop gain, correct? So if you are increasing the loop gain by some factor alpha, your non-linearity is reducing by a factor alpha cube. So like if there is some transconductor in a feedback fashion, so basically you can reduce the non-linearity either by reducing this ratio, or by reducing by increasing the loop gain. So in a feedback system, either you can make the transistors more linear, or you can increase the overall loop gain, so that even if the transistors are not that linear, but since the voltage swing at the uh, virtual ground is so low that like the output nonlinearity is still very low. Are you getting this? Now
Yes, sir.
if you had to if you try to increase the linearity of the transistors, in that case G3 by Gm would have been reduced, but the non-linearity would have reduced linearly only, like because VO3 is directly proportional to G3 by Gm. Okay, so in this case there won't be that amount of difference, that amount of improvement visible. However, if you would have tried to increase uh, Gm into Ri's value by alpha, you see that the nonlinearity reduces by 3 times. Okay, so like in feedback systems, you can get away with slightly nonlinear element elements by having a high loop gain. Are you getting my point?
Yes, sir. Yes, sir.
Now, so how you can increase Ri times GM? Like you can either increase Ri or increase GM. So if you try to increase GM to a very large value, what will you do? You will have to. How will this GM be made? Let's say it was a common source or common source amplifier, or maybe some there. Basically, this will be implemented by a transconductor, right? So let's say how will it be implemented? Let's take example of a single ended GM. So this is, let's say, Vi. This is output is V out. So this is basically a voltage controlled current source, right? The transconductance of this transistor, let's say, is Gm. So if you try to increase Gm, how will you increase it? By increasing the current that is being pushed into this transistor, right?
Yes, sir.
So in that case, you will be burning more power. You will have to burn power. So to increase linearity, either you burn power, or other way would have been that okay, I won't burn. So other way is like increasing resistance, because if you increase resistance, your power consumption won't increase, is it?
Yes, sir.
Resistor is a passive element. If you increase the value of resistance, your power consumption shouldn't have increased. So why can't you make infinite resistors and have no non-linearity at all?
Because of size constraint, passive element.
Let's say there was no size constraint also. Let's say you could maybe have a very element with a very high sheet resistance.
But as a designer, I previously also you take example on common sources. At that time also, we have to choose as
Okay,
a designer.
that is one thing. So here, even if here that issue is not there, because see here, if you see the complete circuit diagram, it can be mentioned and can be made in such a way. So there is some current source and RF, RI, and this is the input. So let's say this is biased in this way. Okay, let's say it's biased properly with this. Let's not worry about the biasing circuit at this point of time. So it's something like this. So in this case also, let's say you increase the R value of Ri, value of RF, the value of common mode wouldn't change, right? Let's say it's something like this, and there is some biasing resistance that is giving some Vg over here, or no, not like this. There is some RB which is a very very huge value. Or let's not worry about the biasing of this right now. Let's say this is properly biased by itself only. So in this case, changing Ri wouldn't change the common mode and all. So what is the problem over here is what is the noise, thermal noise given by these transistors?
4 kT, yes, sir.
Okay, so if you increase this value to a very high extent, what will happen is your noise floor will increase.
Yes, sir. Correct, sir. Correct, correct. Yeah, I get the
Okay,
point. Uh,
so if your noise and if let's say your noise is increasing, what you will have to do?
uh, Mm,
You
sorry.
will eventually have like you cannot so you will have to let's say put a higher signal swing at the inputs to accommodate that so that the signal to noise ratio is high. Now if you if you are to accommodate a higher signal swing, you will have to increase the like VDD of this like this VDD is there. So this VDD you will have to increase the power supply so that the system doesn't get saturated. Then again you are increasing the power consumption. So like again there are two choices you will have to see. So basically RI will more or less be fixed by the noise constraint. So the noise at the output will be sum of this 4 kT RI plus 4 kT RF, and this like based on whatever total noise you can tolerate, you will choose the value of RI. What gain you want from this amplifier, based on that you will choose that gain times RI as RF, and then RI and RF will be fixed. Now whatever distortion numbers you need, based on that you will choose the value of GM. Okay, and this will give you idea of how much power you are going to burn to make this complete circuit. Are you getting my point?
Yes, sir. Yes, sir. The same way what you thought, no, sir. I implemented also, sir. For common source amplifier, you thought, no, sir.
Yeah, yeah, you implemented.
Yes, sir. Actually, I get selected also. Uh, this one common source. I mean, that
Okay, so
non-linear term.
okay, so you implemented that common source thing and got selected in that IIT Bombay some.
eSIM, sir. eSIM.
Okay, okay,
I don't know,
congratulations.
sir. Not only one thing, sir. I mean,
Okay, we can discuss about it later.
yes.
Let's continue the course material for now.
Yeah, sure, sir.
Yeah. So now other thing is, so we did it on a memory-less system. So in this we got these results. Now we will try to do the same thing on a system with memory. Okay. So let's say there is some input Vi. So we will take the case of a low pass filter, first order low pass filter.
Sir, sorry for interruption. Interruption.
Yeah.
Sir, for week 11, sir, in the exam, they won't ask about the plot, no, sir. They will ask about first order, second order, third order terms only, no.
Mm, yeah, I am not very sure. Like, if is the instructions given for that for the exam,
Sorry. Yeah, exam hall ticket also came, sir.
and you
Next
are not
Saturday.
supposed to carry any laptop or something, right?
Nothing, sir.
Okay, then it will be completely calculation based. So like the plots and all won't be asked. Like, obviously.
Yes, sir. Means, sir, I just recall, sir. First, we will find out first order, then we will find out we make the signal input source. Uh,
For zero. Yeah.
yes, input voltage, make it as ground, and we'll find out. We inject current source. First find out second order. If second order is mentioned,
Yeah, then third order, you will inject the third order
mm,
term as well as the cross term with the cross term of second order and first order. So yeah, so on you will carry on like
yeah,
this.
that's how that V01 and V02 V03 will form, no, sir.
Yeah,
While we're asking the output voltage, we have to add entire thing.
yeah, you have to add all of three.
All of three. Okay. Sir, and at the time you said, no, sir, that weak non-linearity will, when gate voltage comes out of the saturation, that weak non-linearity will be strong, no, sir.
No, that case it won't be a weakly nonlinear system. Then it basically it is saturation. You don't call it as weakly nonlinear system. weakly nonlinear system can be called only by the time the GM is substantially higher than G3, or G1 is substantially higher than other these things. Now, if it is coming out of saturation, that means your system is like this G3 and all will keep on dominating. So, like what you can think of is this way: like if you see it, if you see a time domain waveform, and it is like you can see clearly see the clipping in the time domain waveform. That means your transistors are coming out of the saturation region, and you can't analyze it with current injection. So you will have to simulate and do.
Yes, sir. Oh, sir, what are the benefits while knowing the weak non-linearity, sir?
See, that's what, right? We worked out this equation and got to know what design constraints we have, or like in the we 2 weeks before we did the same for the common source. So in common source, we saw that the non-linearity is directly proportional to the overdrive voltage. So these kind of design equation you get, based on that you can decide like what trade-offs you have to make and all those things.
Yes, sir. Is there any benefits, sir, while implementing this
That's what
in
I
terms
told.
of
No, uh,
and
sorry,
in
benefit of.
benefits of while implementing non-linearity? What are the benefits we can do, sir? May means that overdrive voltage, if we don't maintain, that will be a triad decision, not like, in terms of application. But how can we say, sir?
No, this like so you have to increase the linearity. I mean,
Yes, sir. Definitely. That is we have system must be linear. Then only, yeah.
yeah.
No,
So what's benefit you are exactly asking? I am not able to understand.
yes, sir. While implementing that weak nonlinearity, for example, while taking a common source as a common source amplifier, sir, while finding that weak nonlinearity, after knowing that after knowing that nonlinear term harmonics and all, while implementing these, we at the last we'll increase that. Actually, that so small signal gain we can't increase, no. So the second term will increase. Based
No,
on this, we will decrease that non-linear term, I think. Uh, while doing this, I mean, that non-linear term will get, is there anything, sir, rather than this?
so yeah, basically it's that if you
The
uh,
non-linearity get will be linear, sir. I mean, while injecting that current source also, we make it as a linear term only. The second order also.
yeah,
Yes,
so
sir.
that is the procedure. I mean, that procedure you follow. So in the week, it was the reason behind that procedure was given, and that procedure, if you follow, you get you can analyze a system that has non-linear terms in it. So that is the benefit that you get.
Any more benefits, sir? While in application part, you will get no, sir. You will know, sir.
So this is the application of this. So basically, if you analyze a system, you get some. So this can be used in some design equation. For example, this can be used as a design equation. Here you get like in this design equation, you come to know like what terms you can play with to increase the nonlinearity, and based on that, you can decide like what is the optimum way of increasing the in making the system linear. For example, if in this, if you can see, if you like simply increase the linearity of the transistors, its impact will be lesser. However, if you increase the loop gain of the system without touching the transistors linearity, the impact on the linearity will be much higher. So these kind of benefits you get while by doing like hand calculations.
Sir, analytical only we can do, no, sir. We cannot do in code format, right?
No, you can make the code also. What is the issue? You can basically, if you want to do that, you can. So you can have this thing, no? Where is it? So you can make this complete circuit in MATLAB or in LT Spice or Cadence, whatever you want to, and you can run the system. that basically can be used to verify your hand analysis.
Yeah, okay, okay. I mean, that non-linear term only, sir, anything, any more, sir?
Uh, okay, we will discuss your doubt later.
Oh,
Like you can mail the doubt. I mean, I'm not exactly able to understand what you are asking. You can mail that out and I will go through it. Okay, you can ask it on the forum. Okay, so now we will look at another system that is a system with the memory. So in this case, let's say RI, we had this RF and then a parallel capacitor also. Okay, so let's say this is CF and this is output. So again, the exact same procedure we will follow. What was the procedure of finding the ground voltage VG? So first we assume that let's say this was an ideal op amp. In that case, we will find out the output voltage. What is the output voltage? Can you tell? Had the op amp been ideal, what would have been the voltage?
yes, sir. Minus, oh yeah, it will be RF and CF is parallel, right?
Yeah.
Oh,
So uh,
by RA.
it will be minus of
Minus Z by
yeah.
RI, sir. That will be
What
different.
is that? What RF upon 1 plus SCF times RF, correct?
Yes, sir. Perfect, sir.
By RI into VI. So this is equal to minus RF by RI to 1 plus SCF RF into VI. Okay, this is the output voltage. Now again, same thing will happen. You will what will be the current that is flowing in this direction? That will be I will be equal to V naught minus Vg into 1 by Z, correct?
Yes, sir.
Okay, so what is 1 by Z?
Minus RF, yeah, RF by 1 by 1 plus S into
1
CF into RF, right?
CF RF
Mm.
upon RF. Okay, so now again, V naught is much greater than Vg if the loop gain is high enough. So in that case, what will happen is I is approximately equal to that is basically equal to Gm times Vg minus of Gm times Vg is approximately equal to V naught into 1 plus SCF RF upon RF, correct?
Yes, sir.
So this is equal to
VG.
of Vi into RF by Ri into 1 plus SCF RF into 1 plus SCF RF upon RF. So this again comes out to be minus Vi by Ri. Okay. So in this case, it so happens that this uh, voltage Vg. So this is equal to Gm times Vg. So Vg again comes out to be minus Vi upon Ri times Gm. This is the same as that you were getting in that case, on the initial case. Okay. Now what you will do is Vi basically will be cubed. So what? So now again you will short the input. So now this will be Vg hat. So this will be Gm times Vg hat, and this will be Rf and Cf, and you will inject G3 into Vi upon, sorry, again here negative sign won't be there. So okay, so again when you inject this, most of the current will flow in which direction? It won't flow in this direction. Most of it will flow in this direction. So let's say this is some IRF plus ICF, and this is some IG. So IG will be much greater than IRF comma ICF. So most of the current will flow into the transconductor, and if the current is flowing into transconductor, so you can write that G3 times Vi upon Ri into Gm whole cube is approximately equal to minus of Gm times Vg hat. Okay, so again Vg hat is basically equal to Gm by G3. So in this case, it so happens as this is same as the previous. Now, what is the case is, now the further analysis will depend on what is the value of Vi. For example, if Vi is a single tone, Vi is, let's say, sine omega t. Okay. Now, if sine omega t is there, what will be there in the Vi? Vi cube, sorry. So Vi
Yes, sir.
cube,
Yes, sir. That equation will come now, sir. That sine 3 theta.
yeah.
Two
So
two
have
hormones will be present.
will
DC term
have
will be not present.
DC term will be not present. Correct. So omega will be present and 3 omega term will be present.
Yes, sir.
Okay. Now what you have to do is like if let's say you need to find the third harmonic. So which particular term you will be interested in? 3 omega, right?
Yes, sir. First order,
Okay.
third,
The 3 omega term you will be interested in. So like if sine omega t is there, sine omega, so in sine omega cube t, how can it be written?
yes, sir. It would be written like yes, sir. Recently only I did the assignment.
Can you please tell?
Yes, sir. 1 minute.
Otherwise, to recalculate it.
No, no, sir. Already I had done, sir. 1 minute. Sir. Victor. Yes, sir. 3 by 4 sine theta
4
minus 1
t
by 3, 3 by 3 sine theta, sir. 1 by 4, 3 sine 3 theta.
sine 3 omega t.
Yes,
Okay. So we are interested in this finding the value of this term, correct?
yes, sir.
So what we will do is so
We make that current source and we'll find how that is.
so now you know Vg hat. What is Vg? So what is the this only? So let's say Vi was a sine omega t. So the third harmonic component will be third harmonic component in this will be, let's say we call this Vi3 will be minus of 3 sorry minus of a by 4 into sine 3 omega t, correct?
Yes, that current direction will be reversed, sir.
Yeah. Okay, I am just talking about Vg hat. Vg hat, the third harmonic component in Vg hat will be equal to minus Gm upon G3 into a cube by 4 cube is 64 upon Gm cube Ri cube into Vi cube. Okay, sorry, not Vi cube, into sine 3 omega t, correct? So
Yes,
this
sir.
minus go away. So from here, now what you can do is, this is Ri, this was grounded. You have Vg3 hat over here. Now, if Vg3 hat is there, what will be the capacitance? The impedance in the capacitance. This will be 1 upon J3 omega Cf, correct?
Yes, the capacitance value will be get changed.
RF.
According to that V03
So
will also change.
yeah, this won't be omega previously, like while finding the virtual round in the linear circuit, we use this, its impedance was 1 upon j omega cf, but in this case now it will be 1 upon 3 j omega cf. Okay. So yeah, now Vg cube and this is gm into blah blah blah. So now what will happen is the output voltage will be Vg hat 3 into 1 plus uh, Rf upon Ri into 1 plus J3 omega Cf Rf. Okay. Are you getting it?
Yes, yes, sir.
So it's basically like KCL, like Vg cube over here, Vg3 over here. This current will be Vg3 upon Ri, and then the same current will flow through this. Then you can find the output voltage V out due to that. Okay, so with that procedure, you can get to this value. So now what you have is you have this Vg3. So basically you can substitute this complete value over here. So final, the third harmonic you get as Gm by G3 into A cube upon 64 Gm cube Ri cube sine 3 omega t. So we are only talking, let's say, about the magnitude. So this will be this magnitude you can calculate as, just a minute. So this will be, if you take Rf by Ri as a common factor. So here it will be Ri by Rf into 1 plus G omega Cf Rf plus 1 divided by 1 plus, sorry, it is J 3 omega Cf Rf its whole magnitude. Okay. Now, this is what will be the third harmonic magnitude, and we will have its cube. No, we won't have its cube. So, sorry. So, now what will happen is that this term over here. So, if you try to compute your HD3, what will happen?
Sorry, sir.
So, uh, if you try to compute the if you try to see the third harmonic strength with frequency, how will it vary? So it will it will be constant for some time, but when this 3 omega term hits, so what will happen? It will start dipping down, and then again, when this zero hits, it will become some constant. So it will look something like this. Okay, here this term will be equal to 1 upon 3 CF RF times CF, and this term will be equal to corresponding to this zero. Okay, so any other doubts?
Yes, no, sir. Sir, yeah, week 12, sir, we need to take into consideration for week 12 lesson, week 12.
Huh?